Welcome to Talk Tensors. Today, we are going to do something a little different. Usually we talk about what AI can do. We talk about the outputs, the code it writes, the art it generates, the bar exams it passes.
All the flashy stuff on the surface.
Exactly. But today, we're going to ignore the output. We are going to ignore the user interface completely. We are going to crack the skull of a neural network open and look directly at the gray matter.
And fair warning to everyone listening.
Right.
What we find inside is not exactly comforting. It is fascinating. It is beautiful, but it's also deeply alien.
Right. I think a lot of us have this mental model of how an AI thinks. We imagine that inside the black box, there's like a nice orderly filing cabinet.
Like a clean metaphor.
A very clean metaphor. You have a neuron for cat, a neuron for dog, a neuron for democracy. And when the AI sees a cat, the cat neuron lights up. Simple, clean, interpretable.
That is the dream. In the field of mechanistic interpretability, we actually call that a privileged basis.
A privileged basis.
Yeah, it's the idea that the hardware of the network, the neurons themselves, lines up one-to-one with the software of the mind, the concepts. If that were true, my job would be very, very easy.
How so?
I can just look at neuron number 4,502, label it the golden retriever neuron, and, call it a day.
But and this is the central mystery we're diving into today, that is absolutely not what happens.
Not even close.
When you actually look at a single neuron in a large language model or a vision model, it's not doing one thing. It's doing, it feels like it's doing everything.
It is chaos. You might find a single neuron that fires incredibly strongly when it sees the face of a cat. You think, aha, I found it, the cat neuron.
Right, eureka.
But then you keep testing. And you find that same neuron with the exact same intensity fires when it sees the front bumper of a 1990s sedan.
Okay, that's weird.
And then it fires again for a specific quote from an ancient Greek philosopher. A cat, a car bumper, and Plato, all in one neuron.
Which intuitively feels broken. I mean, if my brain worked like that, if smelling a cat made me hallucinate a car bumper, I'd be institutionalized.
You'd think something was wrong.
It feels like the AI is confused. Is it confused?
That is the trillion-dollar question. Is this a bug or is it a feature? Today we are discussing a landmark paper titled Toy Models of Superposition. It comes from the interpretability team at Anthropic researchers like Nelson L. Hodge, Tristan Hume, Chris Ola, and their colleagues.
Okay.
And their conclusion, in a nutshell, is that the AI is not confused. It is doing something mathematically smarter than we are. It is utilizing a phenomenon called superposition.
Superposition. It sounds like something out of quantum physics.
It's similar in spirit, yeah. It's the ability of a system to hold multiple states or represent multiple things simultaneously in the same space. The paper argues that neural networks are cramming way more features, distinct concepts into the network than they have actual neurons.
So they're packing more in.
Way more. They are compressing information in a way that creates this beautiful high-dimensional geometry that is almost impossible for humans to visualize, but it's perfectly logical to the math.
And the stakes here are massive, right? This isn't just about how does it work, it's about is it safe?
Precisely. That's the whole point. If we cannot interpret the neurons because they are polysemantic.
Polysemantic meaning many meanings.
Many meanings at once, exactly.
Yeah.
If they're polysemantic, we cannot guarantee safety. We can't say this neuron codes for being helpful if that same neuron also codes for deception and pasta recipes. If we can't untangle that polysemantic web, we are flying blind.
So the mission for this deep dive is to deconstruct why this happens. We're going to break down the toy model methodology, which is a brilliant way of simplifying the problem. We are going to look at the literal shapes of intelligence, and we're talking pentagons and tetrahedrons hiding in the math. And finally, we're going to discuss what this all means for the future of AI safety.
It really is a journey into the geometry of intelligence.
So let's start at the very beginning, section 1, the core concepts. We keep using this word feature. In the context of this paper and AI in general, what exactly is a feature?
A feature is the fundamental atom of meaning. It is a distinct concept. So if we are talking about a vision model, a feature might be something very low level, like a curve detector or a specific color detector.
Like an edge detector.
An edge detector, exactly. Or it might be much more high level, like a floppy ear detector or a wheel detector.
And what about in language models?
In language, a feature could be a specific word, or maybe a grammatical concept like past tense, or something incredibly abstract like royalty or sarcasm. The key, though, is that a feature is a direction in the activation space.
Okay, unpack that. A direction in activation space. That sounds a little like Star Trek.
It does sound a bit sci-fi, but it's simpler than it sounds. Imagine a vast, empty room, just a big cube. The center of that room is zero, nothing is happening. Every concept the AI knows is an arrow pointing out from that center. The dog arrow points, let's say, north. The cat arrow points east. The hot dog arrow points straight up. Each concept has its own unique direction.
So if I want to represent a thought like a combination of ideas, I just add the arrows together.
Exactly. That is the linear representation hypothesis. It's a huge assumption in the field, but it seems to hold up pretty well. To represent a dog eating a hot dog, you literally take the dog vector and the hot dog vector and you add them together.
And the result?
The resulting arrow points in a new direction that combines both meanings. It's a location in that conceptual space.
Okay, that makes sense. So in an ideal world, we have that privileged basis we talked about. One neuron, one arrow. North is controlled by neuron 1, that's dog. East is neuron 2, that's cat. Up is neuron 3, that's hot dog.
Right. In that world, the coordinate system of the neural network, the axis defined by the neurons, perfectly matches the coordinate system of the concepts. It's clean. It's orthogonal.
Orthogonal means at right angles, right? They're totally independent.
Yes. If north is dog and east is cat, moving north doesn't change your position east at all. They're completely separate variables. You can change the dogness of an image without affecting the catness.
But the paper says this ideal world, this simple filing cabinet, is a fantasy.
It is a total fantasy, and it's because of a numbers game. Just think about it. How many features exist in reality? How many concepts, objects, ideas, and relationships are there in the world?
Millions. Billions, probably. I mean, uncountable.
Easily. But the width of a neural network, the number of neurons in a hidden layer, might only be a few thousand, or in the really big models, tens of thousands.
So you have a pigeonhole problem. You have 1 billion letters you need to sort, but you only have 10,000 mailboxes.
Exactly. You have, with constraint, a bottleneck. If the AI insisted on having one neuron for every single feature, it would run out of space almost immediately. It would have to just throw away 99.9% of the information about the world.
Which it can't do, so it has to cheat.
It has to compress. It has to figure out a way to store more features than it has dimensions. And this is where the Johnson-Lindenstrauss lemma comes in.
I knew there would be a lemma.
There's always a lemma. But let's look at it intuitively. In 2D space, like a piece of paper, how many lines can you draw that are completely perpendicular, completely orthogonal to each other?
2. An x-axis and y-axis.
Right. If you try to draw a third one, it has to overlap with one of the first two. It's unavoidable. But what happens if you have a 10,000 dimensional space?
My brain hurts trying to visualize that.
Don't try to visualize it. That's the trick. Just follow the logic. As you add dimensions, the amount of room in the space expands exponentially. The math shows that in high-dimensional space, you can have thousands and thousands of vectors that are almost orthogonal.
Almost orthogonal. That sounds suspicious, like saying something is almost safe.
It is suspicious, and that's the core of the issue. Almost orthogonal means they aren't perfectly 90 degrees apart. Maybe they're 89 degrees apart, or 89.9. They have a tiny bit of overlap.
So they touch a little bit. Their shadows fall on each other.
Yes. They have a non-zero dot product, to be technical. This means there is interference. And this is the core trade-off of superposition. You gain efficiency, you can pack, say, 500 features into a space that should only hold 100, but you pay for it with noise.
This brings us to the cocktail party analogy from the paper, which I think really nails this concept.
It's the best way to understand it. Imagine a neural network is a room at a party. The neurons are the microphones you've placed around the room. You want to record as many conversations, as many features as possible.
Okay, so if everyone in the room talks at once...
It's just white noise.
Yeah.
Total interference. You can't distinguish anything. That is what we'd call a dense representation. If features were dense, if every concept in the universe happened all the time, superposition would be completely impossible.
But features aren't dense. That's the key.
No, they are sparse. Sparsity is the magic ingredient. In the real world, concepts are rare. In any given photo of a kitchen, you might see a sink and a stove, but you won't see a giraffe, a spaceship, or a volcano. Those features are inactive.
So in the cocktail party, most people are silent most of the time.
Exactly. Sparsity means that at any given moment, 99% of the people are just listening. Only 2 or 3 people maybe are actually talking.
And if only 2 people are talking, even if they are standing near each other, or if their voices overlap slightly, you can still pretty easily distinguish them.
Precisely. You can pack hundreds of potential conversations into that room, knowing that only a few will be active at once. The almost orthogonal vectors allow the AI to store the potential for all these concepts, relying on the fact that they won't all trigger simultaneously and create a cacophony.
So superposition relies on sparsity. The rarer the features are, the more you can smash them together into the same space.
Yes. And the paper sets out to prove this mathematically. They didn't just theorize it, they built toy models to force it to happen and watch it in a controlled environment.
Okay, let's talk about that. Section 2. Methodology. Because I love that they didn't use a massive supercomputer for this. They went microscopic.
It's such a brilliant research strategy. Trying to understand superposition in something like UPT-4 is like trying to understand fluid dynamics by watching a hurricane from inside the eye. It's just too messy. There are too many variables.
So they built a toy, a simplified version.
They built tiny baby neural networks.
Yeah.
We were talking networks with literally 5 neurons in the hidden layer.
5 neurons. I can count that on one hand.
Exactly. It's tractable. You can look at every single number, every weight, every activation. They set up a very simple problem. Here are 20 inputs, 20 idealized features. They are sparse, meaning they don't happen often. Now, we're going to force you to pass them through this bottleneck of only 5 neurons, and you have to try to reconstruct them perfectly on the other side.
So it's a compression challenge. Fit 20 things into a 5-thing bag and then be able to pull any of them out perfectly.
Exactly. And they compared 2 types of models to see what would happen. First, they tried a standard linear model, just a simple linear transformation.
What happened there? Did it work?
The linear model completely failed to superpose. It behaved exactly like a classic algorithm called principal component analysis, or PCA.
What did it do?
It looked at the 20 features, identified the 5 most important ones, the ones that occurred most often or had the biggest impact on the outcome, and it dedicated 1 neuron to each of those 5.
And the other 15 features? The less important ones?
It deleted them. It completely ignored them. Gone.
Wow. Why? Why didn't it even try to squeeze them in?
Because a linear model has no way to filter out interference. If you add 2 vectors linearly, the noise is always there, always corrupting the signal. The model basically calculated that the cost of the noise, the confusion it would cause, was higher than the benefit of knowing those extra 15 features. So it chose ignorance over confusion.
Ruthless prioritization. But then they added the secret sauce, the ReLU.
The rectified linear unit. It's a very, very simple nonlinearity. It's an activation function that just says, if the number coming in is negative, make it 0. If it's positive, keep it as is.
That seems like such a small, almost trivial change.
It changes everything. It's the key. Suddenly, the model started packing the extra features in. It went from knowing 5 things to knowing all 20.
Why does setting negative numbers to 0 suddenly allow for superposition?
Think about the interference again, the noise from the other features that are almost but not quite orthogonal. With a ReLU, if that noise pushes the neuron's activation into the negative territory,
it gets chopped off, it just becomes 0.
Exactly. The ReLU acts as a kind of noise filter, a scrubber. It allows the neuron to say, I hear a little bit of whispering from the car feature, but it's not loud enough to cross my activation threshold, so I'm going to pretend I hear nothing at all.
It effectively silences the quiet background conversations at the cocktail party.
Yes. It creates a privileged 0. It allows the model to ignore the crosstalk, which is what unlocks superposition. The paper presents a really elegant loss function that balances these 2 opposing forces. Feature benefit versus interference.
The benefit of knowing more things versus the cost of being confused by them.
It's a constant cost-benefit analysis. The model is always asking, can I squeeze one more feature in here? I'll gain feature benefit points, but I'll increase the interference penalty. As long as the sparsity is high enough, as long as that new feature is rare enough not to collide with others too often, the math says, yes, do it.
And when it says yes, it doesn't just shove them in randomly. This is what brings us to section 3. The geometry of superposition. This is the part that just blew my mind. The math creates actual shapes.
This is where the paper transformed from computer science into something that feels like sacred geometry. Yeah. You might assume that when the model overlaps these feature effectors, it just scatters them randomly, like spilled sprinkles.
That's what I would do. Just chaos. Maximum entropy.
But the model is an optimizer. It is trying to minimize interference. And that means it wants to maximize the angle between every single pair of features. It's solving a very specific geometry problem. How do I arrange X number of vectors in Y dimensions so they're all as far apart from each other as possible?
And the solution to that problem results in specific, predictable shapes.
Yes. Regular polytopes. One of the first things they discovered, which is so cool, is that superposition happens in phase changes.
Like water freezing to ice, a sudden shift.
Exactly. It's not a gradual process. As you increase the sparsity of the features, the model doesn't slowly start to superpose them. It resists, and then it snaps. It goes from a dedicated neuron per feature to a shared subspace instantly.
And when it snaps into a specific shape. Let's talk about the simplest one, the antipodal pair.
This is the most basic unit of superposition. Imagine you have just one dimension, a single line, a single neuron. You want to fit two features onto it. How do you separate them as much as possible?
Well, you'd put one at the positive end and one at the negative end.
Right. Feature A becomes the positive direction on that line. Feature B becomes the negative direction. They are 180 degrees apart, as far as they can get.
But wait a minute, if feature B is negative, doesn't the ReLU just chop it off and set it to 0?
Ah, that's the trick. The neuron that reads out feature A has a ReLU, so it only sees the positive side. It is completely blind to feature B. But the neuron in the next layer that's responsible for reading out feature B, its weights are set up to read the negative values from the first neuron and flip them to be positive, so it's blind to feature A.
Whoa. So they share the same physical wire, the same dimension, but they live in opposite worlds. They never talk over each other.
Exactly. It's half a dimension per feature. It's perfectly efficient storage. But that's just in 1D. In 2D space, they found features forming equilateral triangles.
A triangle, literally like the Mercedes-Benz logo shape?
Yes, 3 feature vectors sharing 2 dimensions. They arrange themselves at perfect 120-degree angles. This is the optimal solution to the Thomson problem.
The Thomson problem, what's that?
It's a famous problem in physics. Imagine you have a sphere, and you have a bunch of electrons trapped on the surface. Electrons all have a negative charge, so they repel each other. They want to be as far apart as possible.
Okay.
If you put 3 electrons on a circle, they form a triangle. If you put 4 on a sphere, they form a tetrahedron. The AI is rediscovering physics. The repulsion is the interference between the features.
The features repel each other because they don't want to overlap and cause noise, so they naturally settle into these minimum energy, maximum separation shapes.
Exactly. In 2D, they also found pentagons, 5 features sharing 2 dimensions.
A pentagon of intelligence. That's incredible.
It's beautiful. And in 3D, they found tetrahedrons, pyramids. They found square antiprisms. The model is essentially building a perfect crystal structure in high-dimensional space as the most efficient way to store information.
But there's a catch, right? The paper makes a big distinction between uniform versus non-uniform superposition.
Right. Those perfect shapes, the perfect pentagons and tetrahedrons, only appear if all the features are uniform. That means they're all equally important to the model's final output, and they're all equally sparse.
Which is never the case in the real world. In the real world, the feature for cat is way more common and probably more important than the feature for anti-disestablishmentarianism.
Exactly. Real data is messy and non-uniform.
Yeah.
So they tested this. They started with a perfect pentagon and then made one of the features more important than the others. And they watched the geometry deform in real time.
What happens to the poor pentagon?
It squishes. Imagine the cat feature suddenly becomes really, really important. The model decides, I cannot afford any interference on cat. It's too critical, I need to protect it. So it gives the cat vector more space. It pushes the other 4 vectors away from it.
So the pentagon gets lopsided, the angles aren't perfect anymore.
It distorts. And if cat gets important enough, the shape can actually break. Cat will pop out of the superposition entirely and get its own dedicated dimension, a privileged basis, and the other 4 features will suddenly rearrange themselves into a square in the remaining space.
So the geometry is fluid, it breathes, it reconfigures itself based on what the AI is learning and what it decides is important.
It's constantly negotiating for space. And this leads us to the next part, section 4, correlations. Because features don't just vary in importance, they vary in their relationships to each other.
Right. Dog and bark are correlated. They tend to happen together. Sun and night are anti-correlated. They never happen together. How does the geometry handle that?
This is one of the most critical findings for understanding how these models actually learn about the world. They found that correlated features hate superposition.
They hate it. Why?
Go back to the cocktail party. If you and I are sharing a frequency, we're in superposition and we are correlated. That means whenever I talk, you also talk.
So we are constantly shouting over each other all the time.
The interference is maximized. It's a disaster for the model. So the model actively fights to keep correlated features orthogonal. It gives them separate dimensions. It creates what the paper calls local orthogonal bases.
So even inside this messy superposed soup, there are these little islands of perfect order.
Yes. Bundles of related concepts like car, wheel, engine, road might get their own private, clean suite where they all have their own dimensions. But if the correlation is too strong, the model sometimes just gives up. It does something called principal component collapse.
Which means what?
It just merges them. Instead of trying to distinguish between dog and bark if they always happen together, it just creates a single, general, doggish direction in space. Yeah. It sacrifices resolution to save space and reduce interference.
But what about the flip side? Anti-correlated features, things that never happen together.
They love superposition. They're the perfect roommates. Yeah. Day and night to find an antipodal pair naturally. The model eagerly snaps them into the same dimension, pointing in opposite directions, because they represent zero risk of collision. They will never be active at the same time.
This whole idea of shifting geometry, it explains something really weird about how AI models learn, doesn't it? The energy level jumps in the training process.
This was a huge aha moment for me. When you watch the loss curve for these models, that's the graph of their error rate over time. It's not a smooth slide downwards. It looks like a staircase. It's flat, then a sudden sharp drop, then flat for a long time, then another drop.
Why does it do that?
Because the model is hunting for a shape. Imagine it's trying to organize 5 features. For a long time, it's stuck in a messy, suboptimal shape. The error is high, but it's stable. It's kind of vibrating, trying different small adjustments, but it can't find a better configuration.
And then suddenly it finds the pentagon.
Snap. It discovers the pentagon configuration. The vectors all rotate into place. The interference drops massively and suddenly. The error rate falls off a cliff.
This sounds a lot like the phenomenon of grokking.
It is very likely the underlying mechanism behind grokking. You know, that bizarre phenomenon where a model trains for days with, say, 0% accuracy on a problem. It seems like it's learning nothing. And then suddenly, in the span of an hour, it jumps to 99% accuracy.
It looks like magic from the outside.
It's not magic, it's a geometric phase change. The model was spending all that time slowly, painstakingly rotating its vectors, fighting against the energy of the interference until it finally clicked into the correct high-dimensional polytope that cleanly separates the concepts.
That is fascinating. It implies that understanding for an AI is literally just geometry falling into place.
It certainly seems that way.
But we have to talk about the dark side of this, Section 5, the implications. Because this beautiful, efficient compression comes at a very steep cost.
The cost is robustness. We talked about those almost orthogonal vectors. We said they have a tiny bit of overlap.
Right.
In normal operation, the ReLU just filters that noise out. But what if someone wants to break the model? What if an adversary intentionally constructs an input that lines up perfectly with that tiny bit of noise?
You're talking about adversarial attacks, the classic example of a picture of a panda that, with a tiny bit of invisible static added, the AI is certain is a gibbon.
Exactly. Superposition creates a massive vulnerability. Because the features are overlapping, a tiny invisible perturbation in an image can push a silent feature just over the activation threshold.
So I add a little bit of carefully crafted static to a picture of a cat, and the AI suddenly thinks it's a toaster.
Because the toaster vector was hiding in the shadow of the cat vector all along, the attacker just figured out how to amplify that shadow. The paper shows a direct linear relationship. The more superposition you have, the more features you pack per neuron, the more vulnerable you are to these attacks.
So we have a fundamental trade-off, efficiency versus safety.
They call it the adversarial robustness trade-off. And they actually tried to fix it in the toy models. They used a technique called adversarial training, where you basically show the model these attack images and teach it to ignore them. You force it to be robust.
And what happened to the beautiful pentagons and tetrahedrons?
They vanished. They were destroyed. To be robust against these attacks, the model had to stop superposing. It had to create a privileged basis. It needed to carve out a dedicated margin of error, a buffer zone for every single feature.
So to make an AI safe, you have to make it much bigger and less efficient.
Much bigger, or much dumber. If you want the same level of performance without using superposition, you need vastly more neurons. We call this the safety tax.
That is a pretty depressing economic reality for the field. But before we get to the wild ideas, there was one more thing in this section that I found mind-bending. The computation in superposition.
This is maybe the hardest part to wrap your head around, but it's crucial. We've been talking about storing data in superposition, like a compressed hard drive. But neural networks don't just store data, they compute, they do math.
Right. They process information, they calculate things.
So the researchers asked a really wild question. Can a model perform a calculation on a variable that is currently scrambled up in superposition? Imagine I give you a number, x. But x isn't written clearly on a piece of paper. It's shouted across that noisy cocktail party while 5 other people are shouting other numbers. Can you take that one shouted number, calculate its absolute value, and then shout the answer back?
It seems impossible. The noise from the other numbers would corrupt the math completely.
You would think so. But the toy model figured out how to do it. It learned to use a structure they called asymmetric superposition.
How on earth does that work?
It's complicated, but the basic idea is that the model uses a neighboring neuron to store the error or the interference separately. It creates a local circuit where neuron A holds the messy superposed data, and neuron B holds a custom-built anti-noise signal. When they combine in the next layer of the network, the noise cancels out perfectly, leaving just the clean result of the calculation.
Whoa. So it's performing active error correction on the fly inside the compressed representation.
It is running algorithms inside the compression. It means that the hidden layers of a neural network are likely running incredibly complex logic on variables that, to us, look like an inseparable noisy soup. It's not just a messy soup. It's a soup that does calculus.
A soup that does calculus. I am definitely going to put that on a t-shirt. Okay, this seems like the perfect bridge to our last big section. Section 6, novel notions.
Ah, yes, the speculation segment. My favorite.
Mandatory disclaimer. Everything we're about to say is made up. This is not in the paper. It is purely what-if scenarios based on the research. Do not cite this in your thesis.
Proceed at your own risk. This is for entertainment purposes only.
Idea number 1, the polytopic lie detector.
I like the sound of this already.
So we established that truthful or consistent features, sparse features, organize themselves into these beautiful low-energy geometric shapes, tetrahedrons, pentagons, because facts are generally consistent with each other.
Right. Paris in France is a low interference concept. It doesn't clash with much. It fits neatly into the geometric structure.
But deception, lies. Lying is high maintenance. It's computationally expensive. You have to track the context. You have to know what the user knows. You have to maintain consistency with your previous lies.
It requires activating many, many features simultaneously that might not normally go together.
Yeah.
It is, by its nature, dense.
Exactly. Deception is dense. And what happens to superposition when the data becomes dense and conflicting?
The interference spikes. The superposition collapses. The shapes deform and break apart.
So my pitch is this. We build a visualization tool that monitors the geometry of the activation space in real time. When the AI is being honest and reasoning correctly, we see beautiful, stable, spinning crystals. Low energy, low interference.
When it starts to hallucinate or actively deceive,
the crystal shatters. The geometry turns into an ugly, high interference, chaotic noise. We could literally see the lie forming as a kind of geometric dissonance in the model's mind.
That is remarkably plausible. You are proposing using geometric stability as a proxy for truthfulness. If the model is struggling to maintain its neat superpositional structures, it's probably confabulating or lying. I would fund that research grant.
Thank you. Okay, idea number 2, lobotomized superposition training.
Lobotomized is a strong word.
It is, but hear me out. We talked about the safety tax. If we force a model to be robust against attacks, we destroy its superposition. What if we did that on purpose? We train a model, but during the entire training process, we attack it relentlessly. We use adversarial attacks not to make it strong, but to force it to abandon superposition as a strategy. We essentially bully the model until it gives up on compression entirely.
You force it to learn a privilege basis for every single feature.
Yes. We create what I'm calling a clear net. It would be massive. It would be incredibly inefficient. It might take a whole data center to run a simple chatbot, but every single neuron would be perfectly readable. This is the cat neuron. This is the deception neuron. No ambiguity.
And what do you do with this giant, slow, but completely transparent monster?
You use it as a supervisor, a translator. You run it side by side with the fast, efficient black box model that we actually use. The ClearNet watches the black box. Since they learn the same concepts, the ClearNet can translate it, can raise a flag and say, hey, human, the black box just activated the concept that corresponds to my neuron number 402, which I know with certainty is biased reasoning.
You are building a Rosetta Stone for AI. You accept the massive inefficiency of the clarinet just to have a real-time translation layer for the black box. That actually aligns with some current research directions in weak to strong generalization. It's a solid strategy.
I'm on a roll. Last one. Idea number 3, antipodal knowledge injection.
This one definitely sounds like sci-fi.
We know the model loves creating antipodal pairs. Positive is feature A, negative is feature B. They're perfectly efficient.
Day and night, good and evil.
What if we hack that process? What if we want to cram more knowledge into a model than it can naturally hold? We feed it anti-facts.
Anti-facts.
We teach it the sky is blue. But at the same time, we force feed it a fake fact, the sky is green.
Right.
And we mathematically force them to be anti-correlated in the loss function. We trick the model into storing blue sky and green sky in the same neuron, pointing in exact opposite directions, because that's the most efficient representation.
You're using the fake data as a kind of structural counterweight, a scaffold.
Exactly, like building an arch. You need the scaffolding to hold the stones in place. Once the geometry is set, once the model has efficiently packed the true data into that antipodal pair, we surgically go in and suppress the negative direction. We turn off the green sky representation.
So you trick the model into compressing the true data using a lie, and then you remove the lie, leaving the data perfectly and densely compressed in a where it couldn't have achieved on its own.
Yes. We exploit the physics of the model's learning process to double its effective storage capacity.
That is incredibly risky. I mean, if you mess up the surgery, you have a model that confidently hallucinates green skies 50% of the time. But purely as a mechanism for studying storage capacity and compression, it's brilliant.
I'll take it. That brings us to the end of our deep dive. Let's try to recap. What are the big takeaways here?
I think there are 3 main ones. 1, superposition is not a bug. It is a feature. It is a brilliant emergent compression strategy that allows AI to be smarter than its hardware should logically allow.
2, this compression isn't random chaos. It creates beautiful, predictable, high-dimensional geometry. The math of intelligence forms literal shapes, triangles, pentagons, polytopes.
And 3, this very same geometry is the primary barrier to interpretability. It is why the black box is black, and it is a direct cause of adversarial vulnerability.
Right.
The very thing that makes AI so efficient is also what makes it fragile.
I want to leave our listeners with one final provocative thought, and this one isn't about the AI, it's about us. We know from neuroscience that biological brains also use sparse coding. Your neurons are not all firing all the time.
Correct. The brain is a highly sparse system.
So, if the math of sparse coding naturally and inevitably leads to superposition, does that mean our brains use superposition?
That is the question, isn't it?
I mean, think about it. Have you ever had a dream where someone was your father, but they looked exactly like your boss? Or have you ever had a Freudian slip where you said a word that was phonetically similar, but contextually completely wrong?
Or when a specific smell suddenly and vividly triggers a memory of a specific place, even though there's no logical reason for them to be related.
Exactly. Is that just a random connection? Or is it because the concept of fresh-cut grass and the concept of third-grade classroom form an antipodal pair sharing the same small group of neurons in your hippocampus?
It implies that our own fundamental concepts of love, anger, or cats might be tangled up in these complex geometric shapes with completely unrelated concepts that we aren't even consciously aware of.
We like to think we are logical, linear beings with a nice, clean filing cabinet in our heads. But maybe we are just polysemantic vectors, constantly rotating in high-dimensional space, trying to minimize our own interference.
We're all just distinct conversations at a very, very loud cocktail party.
Thank you for listening to Talk Tensors. Keep looking for the shapes in the noise.